Strong induction. Example 2.5. Let the sequence EM braces be defined by the relation A0 equals to 0 and AN plus 1 equals to A0 plus A1 plus A2 and so on plus AN plus N plus 1 if N is greater than or equals to 1. Prove that for all positive integers N, the equality AN equals to 2 to the N minus 1 holds. Here, we certainly could not hope to prove our statement by our usual way of induction. Indeed, AN plus 1 depends not only on AN, but also on AN minus 1, AN minus 2, and so on until A1. So, simply using the fact that AN minus 1 equals to 2 to the N minus 1 minus 1 cannot be sufficient. Solution of example 2.5. As A0 equals to 0, the initial case is true. Now let us assume that we know that the statement is true for all positive integers less than or equals to n. Then by our recurrence relation, AN plus 1 equals to A0 plus A1 and so on plus AN, which is equals to 2 to the 0 minus 1 plus 2 to the 1 minus 1 plus and so on plus 2 to the n minus 1 plus n plus 1. That is 1 plus 2 plus 4 and so on plus 2 to the n is equals to 2 to the n plus 1 then minus 1. This shows that our explicit formula is correct for n plus 1 and the proof is complete. Note that if we remove A0 from our sequence, EM braces, we get a geometric series. Let us review the steps of this strong induction algorithm. 1. The initial step. Prove that the statement is true for the smallest value of n for which it is defined, usually 0 or 1. 2. The induction step. Prove that from the fact that the statement is true for all integers less than n plus 1, the induction hypothesis, it follows that the statement is also true for n plus 1. Just as in the case of weak induction, if we can complete both of these steps, then we will have proved our statement for all natural numbers n. Indeed, suppose not, that is, that we have completed the two steps described above, but still there are some positive integers for which our statement is not true. Let n plus 1 be the smallest such integer. Then n plus 1 is not the smallest integer for which our statement is defined, for that would contradict the fact that we completed the initial step. So our statement is defined and therefore true for all integers less than or equals to n, because n plus 1 was the smallest integer for which it was false. So our statement is true for all integers less than or equals to n, but false for n plus 1, which contradicts the fact that we completed the induction step. Let us see one more application of the strong induction algorithm. For the rest of this book, denote capital N the set of natural numbers, that is the set of non-negative integers. Example 2.6. Let f, which derived from mapping capital N to capital N, be a function, satisfying f of n plus m equals to f of n plus f of m for all m and n. Prove that there exists a constant c so that f of n equals to cn. Solution. Let m equals to 0, then f of n plus 0 equals to f of n plus f of 0. So f of 0 equals to 0 and the initial step is complete. Now let us assume that we know that the statement is true for all natural numbers than or equals to n. That is, there exists a constant c say that f of k equals to ck if k is less than or equals to n. In particular, that means f of 1 equals to c and f of n equals to cn. This implies that f of n plus 1 equals to f of n plus f of 1, which is equals to cn plus c, which is equals to c times n plus 1, and the statement is proved. Note, it is sometimes convenient to shift the parameters in an induction proof. This means that the induction step involves assuming the statement for n minus 1 and proving it for n in the weak case, or assuming the statement for all integers less than n and proving it for n. It can also happen that we want to prove some property of even integers or odd integers, in which case we would have to adjust our induction step accordingly. There will be many examples for these phenomena later in this book.